Good morning. So today I will be continuing with the design of fixed portal frame. So let me brush up what are all the things that I have done in the last class. In the last class I have completed with the design of one-way continuous line. That is the last but one class. Okay. So in the yesterday's class I took the analysis of portal frame. So portal frame means it is the footing, column and the beam portion. Yes or no? So now, and one more thing. So in the last class, I have calculated what is the width of the beam, what is the breadth of the beam. What is the depth of the beam. And even I calculated what should be the width of the column and what should be the depth of the column. Next, as it is a portal frame, I took the beams first. In beams, what are the loads that is coming on the beams? That we have already calculated. So what was the total load that was coming on the beam? So the total load that was coming on the beam, it was 51 kilonewton per meter. Okay. So now what we will do here is observe. First let me write that particular beam portion, I mean the portal frame portion. It is a fixed portal frame. And one more thing, in design of portal frame, there is one more topic, that is design of hinged portal frame. Here we are doing the design of fixed portal frame. There is one more, it is hinged portal frame. That we'll do later. So now it's a fixed portal frame. I think you people remember one more thing. So the total length it was 20 meter. So at equal spacings, you people were having the beams like this. 4 meter, 4 meter, 4 meter, everywhere 4 meter. This particular distance, it was 8 meter. So now as I am concentrating on the beam, so this is one portal frame. This is one more like that. We are having the columns at all this particular junction. So now I am taking this portal frame. So this portal frame I am taking. So what will be the width? So width it will be 8 meter. Please remember, width it will be 8 meter. What is the total height? In the question they have given, the height of the column till the center of the beam is 5 meter. Let me check it out. Yes, it's 5 meter. So they have only given this. So the height of the column till the center of the beam they have given, it is 5 meter. We have already calculated what is the load that is coming on the beam. So what is the load that is coming on the beam? It is 51 kilonewton per meter. It is 51 kilonewton per meter. Okay. So now what we will do is, so as I am taking up the beam, so what is the final thing that I am in need of? It is the number of bars. If I want the number of bars, I want to know what is the area of steel that I need to provide. If I want to know the area of steel, how much it bends, so bending moment. If I want to know the bending moment, I want to know the loads. Loads I have calculated, I want the bending moment now. So what I will be doing is, so there are many methods to calculate, I need to analyze this particular frame structure. It might be moment distribution method, Carney's rotational contribution method. Like that there are many. So for this particular topic, I will be taking Carney's rotational contribution method to get the PMD values. Okay. So now what I will be doing, let me take up the Carney's rotational contribution method. So here, as it is a total thing, I think this you people know that. If I call the column as I, okay, this we have already calculated. Calculation of moment of inertia. In the last class I have told you people, it is 1.83 times I. We have already calculated this. So now, as it is symmetric in nature, let me take only half of the portion and analyze. Let me take half of the portion and analyze. Okay, so we'll do one thing. Let me write it here itself. I will be considering only half of the portion. So this is fixed. I will be taking half of the portion. I will be showing the continuation now. So the stiffness will be full. Here as I have considered half, the stiffness will be like this. So please remember that. So next, this is A portion. This is B portion. This is 5 meter and this is A, B, C, D. If I call this is C. For time being, I will be calling it as C dash. Okay? So now, instead of calling it as C dash, we will call it as C only. So this is how we need to take the diagram. Okay? So now what I will be doing is, let me calculate the fixed end moments. I think you people know all those things. Yes or no? Let me calculate the fixed end moments. So fixed end moments. FEM. I think while doing the structural analysis, I think you people remember this. Fixed end moments. So MF of AB and BC is 0. What is the reason? Observe here. MF of AB, MF of BA, both are 0. The reason is there is no load acting. Therefore, MF of AB is equal to MF of BA. Both is equal to 0. Okay. So next, MF of BC. MF of BC. I think you people remember. So for fixed end moments, we need to consider it as fixed. So there will be UDL, and this UDL is 51 kilonewton per meter. So there will be one fixed end moment here, one fixed end moment here. I think you people remember it is WL square by 12. This is also WL square by 12. So as it is anti-clockwise negative, as it is clockwise it is positive. So I want MF of BC. So it is anti-clockwise. So MF of BC is minus WL square by 12. So minus 51 into. So what is the L square? So it's 8 meter. So it's 8 square by 12. So what is the value that we are getting for that? So it's minus 272 kilonewton per meter. Similarly, let me go with MF of CV portion. Only half we have considered. Anyhow, let me calculate the fixed end moment. MF of CV. So CV it is clockwise. It is clockwise. So it's plus WL square by 12. So it's 51 into 8 square by 12. So that is plus 272 kilonewton per meter. I think this you people know the lengths. So next, we'll move on with the tabular form. I am just using the Drss rotational contribution method, nothing else. Okay, so first it should be the member. First, it should be the member. Okay, how many members are there? So as we have taken only half the portion of the frame, so I will be taking B portion. So from B, it is BA and BC. I will be taking the portion B. Instead of calling it as member, let me call it as joint. And here I will be calling it as member. So member it is BA and BC. Okay, next I will be going with the calculation of reduction factor. I will be going with the calculation of reduction factor. So where reduction factor, please remember one thing I will be telling. If you just take it as a note, if far end is fixed or continuous, fixed or continuous, then the response reduction factor or reduction factor should be equal to 4EI by L. And one more thing, I think you people know all these things because you people have studied this time in that particularly Drss rotation contribution method. Okay, so if the far end is hinging, if the far end is hinging, then RF I need to take it as 3EI by L. So I need to take it as 3EI by L. So now let me go one by one. So response reduction factor, so I will be calling it as K. Observe here. So I will be going with BA. So stiffness is K. Okay, what is the formula? Observe here. If I consider this as the joint, what is the far end? It's a fixed. So whenever it is fixed or continuous, what is the value that I need to take for K? So it is 4EI by L. And what is the value of I? Observe here. So for BA, so it is I only. Whenever I talk about BC, it is 1.83 times I. So now let me substitute as it is 4EI by what is L? So L value for BA is 5 meter. Okay, so whenever we solve this, we get 0.8 times EI. Similarly, let me go with BC. So BC, it is only half portion I am taking because of symmetry. Because if I analyze for half of the portion, the other half portion will be same. So only half of the portion I will be taking in. So BC. So don't you think that it is continuous? So whenever it is continuous, so then it is 4EI by L. Okay, so half times 4 into EI. I value, it should be 1.83 times I. Therefore, it becomes 1.83 EI by, so what is L? So L is, total is 8 meter. So why we need to take only half of it, no sir? But already I have taken, for total thing it is half. So no need to multiply again. So what is the value? So it's 0.46 times EI. I want the value of sigma K. Sigma K means add these two. So 0.8 EI, 0.46 EI, it is 1.26 EI. Next, the final thing. I want this U, which is given by minus half into K by sigma K. I think you people remember all these things. So it is minus half into K by sigma K. Observe here. K is this. Sigma K is this. So minus half into K by sigma K. If I do it, so you people will be getting minus 0.318 for BA member. For BC member, it is minus 0.182. I think you people know that when I add these two, I should get minus 0.5. So this is how we need to do it. So next, what I need to do? Next, I will be writing a diagram. Let me rub all these things. So I will be rubbing this. This also I will be rubbing. So now what I will be doing is, let me draw a diagram. I think you people remember all those things, I guess. So this is B point. Okay. So C point, it's continuous. So A point is fixed. Okay. So in the left side I will be showing the FEM part. In the right side I will be showing the moment part. I will be telling you. So now what is the reduction factor that we got? So the reduction factor that we got for BA, I mean the U value. So it is, BA value is 0.318 minus 0.318 minus 0.318. So what about for BC? So for BC it is minus 0.128, sorry 182, minus 0.182. Okay, so now what is the value of FEM that we got? So FBA, okay, FAB, both are 0. Please remember that. FEM part I am writing it here. Here also above I will be writing FEM, moment I will be writing down. So here, so for BC, So what is the fixed end moments that we got? So for FBC, not FCB, I am not coming from CB, I am going from BC. So BC. So what is the value? It's minus 272. It's minus 272. I think you people know I need to add this and this. So minus 272, 0. Plus 0. It is minus 272. So now, if I want the moments, what I need to do? So minus 272 into minus 0.318. If I multiply these two, I will be getting one particular moment. And that value is 49.5. 49.5. Please remember how I got this. So it's minus 272 into minus 0.318. So it's 49.5. I got some value here. Okay, I think you people know that whenever there is no load, I am fixed here. So the other moment will also be 0. This thing you people have already studied in your stand. Okay, so now let me multiply minus 272 into minus 0.18. Minus 272 into minus 0.182. So what is the value that we are getting? Sorry, I made a mistake. Actually, this should be 49.5. Okay, this should be 49.5. So observe here, minus 272 into minus 0.318. This is not 49.5. This is 49.5. Minus 272 into minus 0.182. It is 49.5. So minus 272 into minus 0.318. The value is 86.49. 86.49. So this should be 86.49. And one more thing is, actually you need to continue this procedure until the value gets stabilized. I think you people know that. So whenever you do one more step, it may come around 84 point something. Next step 84.2, next 84.2. So whenever the value repeats, you need to stop at that stage. But the procedure is huge. Okay, so that's why what I will be doing. So I will be going with one iteration. Okay, so keeping this particular values, I will be proceeding. So let me calculate the moment about BA. So how to calculate moment about BA? I think you people know a particular formula. When I want to calculate the moment about BA, I mean about this particular point. So it is the fixed end moments at that particular point. It is the fixed end moment at that particular point. Or else we'll do one thing. Let me first go with MAB only. So from MAB, first I will be going with. So MAB. So it is the fixed end moments at that point plus 2 times the near end moments, 2 times the near end moment, not fixed end moment, near end moments, I will be telling which is that, plus the far end moment. So MBA, the far end moment. So observe here, please remember this formula. So what is that? So near fixed end moments plus 2 times the near end moments plus far end moments. So that is the formula. So what is MF of AB? Fixed end moments? It is 0. This line is fixed end moments. It is 0 plus 2 times the near end moment. So near end moment is also 0. So what about the far end moment, not fixed end moment? Far end moment, it is 86.49. So the final value that we are getting is 86.49 kilonewton meter. So for MAB. Okay. Similarly, let me calculate for MBA. Same concept. For MBA also, fixed end moments about that particular point plus 2 times the near end moment plus far end moment. Far end moment is 80. Okay. So now, what is the fixed end moments about BA? So it is 0 plus 2 times the moment about that particular point. So it is 86.49 plus far end moment. Far end moment is 0. So what is this particular value? So it's 172.98. 172.98 kilonewton meter. So now we are left out with the last one, MBC. What about MBC? Same concept. So if I want MBC, so please remember, so it is MF of BC, okay, plus 2 times the near end moment plus far end moment, that is CB. Okay, so MF of BC, fixed end moments, so it is minus 272. It's minus 272 plus 2 times the near end moments, that is 49.5 plus MCB, that is the far end moment. I don't know for time being, let me consider it as 0. So now, what is the value if I solve it that I will be getting? So it's minus 173 kilonewton. It's minus 173 kilonewton meter. So this is how we need to calculate the bending moment. If you know how to do further, you can do one more iteration and stop it. If not, you can stop it at one iteration itself, because whenever I go to the next iteration, the value will be very close and I will be multiplying it with 1.5. So everywhere it will be safe. So no need to worry about that. So this is how we need to calculate the bending moment. So now what I will be doing is, let me write down all these bending moment values in a single diagram. Okay, so that I will be writing it. So I will be rubbing this. So now what I will be doing is, let me consider the frame, and the loading. Let me consider the frame and the loading, and the loading value is 51 kilonewton per meter. So let me write down what are all the moments that we got. So what is MAB? So it is 86.49 kilonewton. So it is clockwise. This is A, this is B, this is C, this is D. So MAB, it is clockwise moment and the value is 86.49 kilonewton meter. Next, what is MBA? It is 172.98. Can I approximately make it as 173 kilonewton? So it is also positive, therefore that is also clockwise. So 173 I will be calling it as. So what about MBC? So MBC is minus 173 kilonewton, minus. So it means that anti-clockwise. So clockwise and anti-clockwise, that will get nullified. So we will be maintaining the equilibrium. So please remember, this is a clue whether whatever we have done it is correct or not. So now, as it is a symmetry, so we will be transferring the symmetry. Here it is anti-clockwise, obviously here it should be clockwise. Here it is clockwise, therefore it should be anti-clockwise. Here it is clockwise, therefore it should be anti-clockwise. So any doubts on that? So this is 86.49. I think all these things you people remember in Tani's rotational contribution method. Let me write the SFD and BMD. Let me first write the BMD. Let me think that I am standing inside. So this particular moment is pushing it away. So it's 89 point something, and here it is pushing it down. So a little bit bigger. This is a little bit smaller because it is 86.49 and here it is 170 something. So this is positive and this one is, so this is also clockwise, that is also clockwise. So no problem. So this is negative. Okay, next, here also the same thing. So it is going in this direction. It is pushing in this direction away. I think you people know, above the line I will be taking it as positive, below the line I will be taking it as negative. Here also the same thing. So here it is pushing it outside, so it is 86.49. So here it is pushing it down, so I will be considering this particular portion. So outside I will be taking it as positive and inside I will be taking it as negative. So next, there is one more. Here also 173, here also 173. So you can take it like this. So it is 173 kilonewton meter. So here also it is 173. This is 86.49 kilonewton meter. Here also it is 86.49 kilonewton meter. So this is also 173, this is also 173. And this side is also 173. But the thing is, if I want to go with the design of beam, so I will be concentrating on this. So there is a new deal. Let me calculate the maximum bending moment. So whenever a beam carrying UDL, what is the maximum bending moment? So the maximum bending moment formula is given by WL square by 8. So W is 51 into 8 square by 8. So the total value that we are getting for that is 408 kilonewton meter. So I think you people know that it comes like this. Yes or no? So this total value is 408 kilonewton meter. Let me write it here. So the total value is 408 kilonewton meter. Now I will be splitting it up. So what do you mean by that? So this distance is 173. Yes or no? This distance is 173. Total 408. 173 will be taken care by this. So 408 minus 173. So this distance it will be. So 408 minus 173. So the value that we are getting is 235. It's 235 kilonewton meter. So this I will be calling it as positive, the other I will be calling it as negative. So any doubts on that? So now keeping this particular values, we need to solve the further problems. So first we'll write one by one. So I will be wrapping this. So let me write down the final bending moment values and all. So I will be writing it like this. So it's final design values. Final design values. So for beam, actually what is the heading? I have taken it as beam only. I was supposed to take up the design of beams. First let me write down the beam, column and footing, bending moment and the dimensions and all. So finally I am doing with the final design values. Beam, what is the breadth that we have assumed? It's 300 mm. So what is the overall depth that we have assumed? 550 mm. Okay, next. The load that is coming on the beam, it is 51 kilonewton per meter. So what is the span of the beam? So span is 8 meter. So what is the maximum bending moment that is coming on the beam? You should never say 408. Observe here, you should never say 408 because this minus value will be taken care by this. Okay, so 173 I need to deduct. So finally this is the maximum value. It's 235 kilonewton meter. We need to design for this particular moment. Because one is negative moment and one more is positive moment. So the overtaken comes and finally we need to design it for 235 kilonewton. Okay, so now, next what I need to do is, so what is, observe here, from the beam I need to transfer load to the column. From the column the load needs to be taken care by the footing. So what is the load that is transferring to the column? So it is nothing but the maximum shear force. Whatever the load that is coming, it needs to transfer to the support. That is nothing but the maximum shear force. So maximum shear force. Maximum shear force is given by, I think you people know that, for an UDL, for a beam carrying UDL, what is the maximum shear force formula? It's WL square by 2. So WL square by 2. So W is 51 into 8 square by 2. So the value that we get, it's 204 kilonewton. It's 204 kilonewton. Please remember, maximum shear force is nothing but the reaction from beam. Reaction from beam. So these are all the things that I want to know. to proceed with the design. So next I will be moving on with the MU at the support and MU at the midspan, because that also I want to know. I will be explaining. So MU at support. MU at support also I want. So MU at support. So support is 173 kilonewton meter. So MU at midspan. So MU at midspan. Because keeping this value I can easily do it. So MU at midspan is 235 kilonewton. This value. This one. So it's 235 kilonewton meter. So this is about the beam. Now let me move on with the column. So what are all the values for columns? So breadth and depth I know. Breadth is 300 only that we have assumed. Depth is 450 that we have assumed for columns. Then please remember, for this column we are having two particular moments. So one is at the top 173 and one more at the bottom, it is 86.49. Always go with the highest value. So MU for column that I need to consider for the design is 173 kilonewton meter. It's 173 kilonewton meter. Next, I want to know the PU of column. What is that? It is nothing but the reaction from beam. Obviously, no? Whatever the load that is coming on the beam, that needs to be transferred to the column in a point load manner, axial force. So that axial force is nothing but the reaction from the beam. So it is nothing but reaction from beam. So that value is 204 kilonewton. So now the last one is the footing. Let me write that and then I will be proceeding with the design of beams. So now I will be rubbing this. So next it is the footing portion. So third one, it is the footing portion. So what is the SBC of the soil that they have given? It's 120 kilonewton per meter square. It is given in the question itself. Okay. So next, what is MU of footing? So MU of footing. What is the bending moment that is coming near the footing? Observe here. So wherever you are having the column moment, and that too the footing will be at the bottom. So this is the moment that you people need to take for the design. That is 86.49. It's 86.49 kilonewton meter. Okay. Next, the last thing is, what is the load that is coming on the footing? That also will calculate so that we can easily proceed with the design. Okay. So now load on footing. So what is the load on footing? So load on footing. What are all the loads that is coming on the footing? The load from the column and the self weight of the column. Yes or no? So both I need to take. So it is nothing but load from column. Load from column plus self weight of column. Self weight of column. Yes or no? What is the load from column? It is nothing but the reaction. So what was the low UDL? I have converted it to point load and I have transferred it. So that is nothing but the beam reaction. It is 204. How to calculate the self weight of the column? Density into volume. So density into volume. Density is 25 kilonewton per meter cube. What is the dimensions of the column? So it is 0.3 breadth into depth 0.45 meter into what is the height? 5 meter height. Okay, so finally if we multiply, the value that we are getting is 229.31. It's 229.31 kilonewton. So any doubts in this? So now we have completed the analysis of portal frame. So analysis of portal frame, we came to know what is the breadth, what is the depth and what is the bending moment that is coming on the beam. and even on columns and even on footing also we have calculated. So now we are left out with the design part. So let me move on with the design part. As it is a portal frame, there are three design parts. So one is the design of beam, one more is the column, and one more is the footing. So first let me take up the design of beams. So now I will be taking up the next step, that is the design of beams. So I have forgotten the step number, just I will be leaving it as it is, design of beams. Now I will be explaining you people one particular concept. So observe here. So as it is a portal frame, on both the sides the beams are fixed. On both the sides the beams are fixed. Okay, so instead of taking it in this particular pattern, let me take it as a single line. I think you people know how it bends. So whenever it is a fixed support, at the supports also you people needs to provide the steel. So the tension will be at the bottom near the midspan and tension will be at the top near the supports. Okay, just imagine that this acts as a T-beam because this beam is monolithically casted with the slab. Okay, so now what I will be writing is, observe here, this is a beam. If I cut it and see it in this direction, I will be writing the beam in this pattern. Okay, so now observe here what will happen. So near the supports, what will happen? The tension is at the top. So the tension is at the top. So it means that, observe here, when the tension is at the top, it means that the neutral axis lies within that. Yes or no? So at the support the neutral axis lies within the flange. Therefore design it as the rectangular section. So design it as the rectangular section near the supports. Near supports the tension is at the top. So this is the tension portion. Okay, so near the support design the beam as rectangular beam. Rectangular beam. So what will happen near the midspan? So near the midspan the tension is at the bottom. So it means that, at the bottom, the tension is at the bottom. So it means that the neutral axis lies within the web. So whenever that is the case, near midspan, design the beam as T-beam. Design the beam as T-beam. This is very, very important. Okay, so as it is a fixed beam, at the support the tension will be at the top, at the midspan the tension will be at the bottom. So at the support you need to design it as a rectangular beam. At the midspan, because as it lies in the web, so you need to design it as T-beam. So that's why we'll take one by one. So next, design of mid-span section. Design of mid-span section. Design of beams, obviously at the supports and at the midspan I need to provide the steel. Now I will be taking design of mid-span section. Soon after this I will be taking the support section. Mid-span section. So I need to design it as a T-beam. Whenever you are designing it as a T-beam, instead of B you need to take it as BF. I think you people remember that. So now what I will be doing is, first let me calculate what is the effective flange width. So this is the flange. So what is the effective flange width? So effective flange width is given by and that is given in page 37 of IS 456. So effective flange width, page 37 of IS 456. So if we use that particular page, so the formula is given like this. BF is equal to L naught divided by 6 plus BW. BW is nothing but the B. So BW plus 6 times DB. 6 times DB. Okay. So now code suggests one more thing. So in page 37 of IS 456, this is very important. So L naught, we need to take it as 0.7 times L. I want everyone to open page 37 of IS 456. It will help you a lot. So I will be opening and I will be reading it out. So here what they explain is, for continuous beams and frames, L naught may be assumed as 0.7 times the effective span. That is very important. It's a continuous beam. Okay, the beam continuously running. So therefore, instead of L naught, I need to consider 0.7 times the effective span. That is very important. So 0.7 times L naught is equal to 0.7 times L. L is nothing but 8 meter. 8 7s are 56. So 5.6 meter. So it's 5.6 meter, or it's 5600 mm. Let me substitute this value over here. So BF is equal to L naught is 5600 divided by 6. So effective BW is 300. So BW is 300 plus. So I am opening page 37. Let me read out what they have given. Actually, it's 6 times DF. Okay, it's not 6 times DB, it's 6 times DF. DF is thickness of the flange. So please make a correction here. It's 6 times DF, where DF is the thickness of the flange. What is the thickness of the flange? It is nothing but the thickness of the slab. It's 150 mm. So it's 150 mm. So if I solve it, so the final value that I am getting is 2133.33 mm. 2133.33 mm. So I got the value of BF. So now let me proceed with the design. I know the bending moment. So next I can go with the calculation of area of steel. So next heading, area of steel. So next heading is area of steel. I think you people know what is the formula to calculate the area of steel. Mu is equal to 0.87 FYAST into D into 1 minus FYAST divided by FCK B into D. Let me substitute. Now, what is the value of Mu that you people will be taking? So, Mu mid-span, already we have calculated the bending moment at the mid-span. It's 235 kilonewton meter. So, that we need to substitute it. It's 235 into, to convert that into kilonewton meter, 10 power 6, 0.87, Fy is 415, AST only I need to calculate. So, the effective depth of the beam is, observe here, effective depth of the beam. What is the overall depth of the beam? It's 550 mm. Let me assume effective cover of 30 mm for the beam. Effective cover of 30 mm for the beam. So then, will you people accept that? Effective depth is equal to 550 minus 30, it is 520. So please remember, so the effective depth is 520 mm. I forgot that, so that's why I'm doing it now. So 415 into AST only I need to calculate, divided by FCK, I think it's 20, breadth as it is a beam, it's 300, effective depth is 520. So after solving it using the calculator, the value that we get here is, so 1282.45 mm square. 1282.45 mm square. So soon after calculation of AST, what we need to do? So we need to calculate the number of bars. Yes or no? Actually, I was supposed to check with AST minimum. Okay, but there is no need to, because the AST is not around 300, 400 or 500 something else. So if that was the case, I would have checked for AST minimum. As it is more, I will be directly going further. So assuming either you go with 12, 16 or 20 mm, but the value is little bit higher, shall I go with 20 mm diabars? So assuming, you can even go with 16, no problem. Assuming 20 mm diabars, 20 mm diabars. So number of bars is equal to 1282.45 divided by area of each bar. So what is the number of bars that we are getting here? So it's 4.08. 4.08 approximately. Let me make it as 5 number of bars. So whatever the area of steel that we got, 1282.45, so we are getting 4.08, but approximately we are providing 5 number of bars. So as we are increasing the steel, let me calculate what is the AST provided. So why I am calculating AST provided? Because as it is a beam, I need to do check for deflection. In deflection, so L by D max, if it is a continuous, 26 times F1, F2, F3. If I want to calculate F1, I want to calculate Fs. Fs is given by 0.58 times Fy into AST required by AST provided. So I will be calculating AST provided. So it's nothing but equal to 5 number of bars I have provided, then area of each bar. So the value that we are getting here is, so it's 1570.79. 1570.79 mm square. So I have calculated the number of bars near the midspan. Let me now go with the number of bars near the support reaction, near the supports. So let me take up the design of support section. So design of midspan section over. Now design of second one I will be taking. So it's design of support section. So I will not be writing this. Design it as a rectangular beam. So I need to design it as rectangular beam. So as usual, directly there is no need to calculate the effective length and all those things. Directly mu is equal to 0.87. Let me calculate the area of steel. So let me directly take up the area of steel. Let me directly take up the area of steel. So same thing, I will not be writing the formula. Directly I will be substituting it. So what is mu at the support? So it was 173 kilonewton meter. Final design values, the heading, under that heading I have written each and everything. What is mu midspan, what is mu support, all those things. So it is 173. To convert that into Newton mm, this one, into 0.87 Fy AST into D is same, 520, into 1 minus Fy AST divided by FCK B into D. So using the calculator, if we solve, so the value that we are getting, so is 1075.21 mm. 1075.21 mm alla, it is mm square. It's not mm, it is mm square. Okay, so as it is a beam, let me calculate near the support how many number of bars I need to give. Assuming, let me go with 20 only. Assuming 20 mm dia bars, number of bars is equal to, so it's 1075.21 divided by pi by 4 into 20 square. So the value that we are getting here is 3.42. Approximately 4 number of bars we need to provide. 4 number of bars we need to provide. Here I will not be calculating the AST provided. The reason is, while doing the check for deflection, deflection will be maximum near the maximum near the mid-span. So that's why for mid-span section, I have calculated AST provided. I will not be calculating for this. Okay, so now what I need to do? I need to go with the stirrups. And all those things I will be continuing it in the next class. For this class, I will be winding up. Thank you.